There is a star burning right now, somewhere in the unimaginable distance, that will be the last star the universe ever creates. After that star dies, no new stars will ever form again, not in 1 billion years, not in 1 trillion, never. The universe will grow darker and colder and emptier until nothing remains but the faint whisper of radiation slowly dissipating into absolute nothingness. This isn't science fiction. This is thermodynamics. This is gravity. This is the inevitable conclusion written into the fundamental laws of physics. Right now, our universe is in its golden age. Stars blaze across billions of galaxies. Life emerges on countless worlds. Energy flows freely through cosmic structures spanning incomprehensible distances. But we exist in a fleeting moment, a cosmic eye blink, before everything changes forever. What if I told you that scientists can calculate with disturbing precision exactly when the last star will die, that they can map the stages of cosmic death with the same certainty that astronomers predict eclipses? The evidence exists in our telescopes right now, in the light from distant galaxies, in the behavior of matter across cosmic time, in equations that describe the ultimate fate of everything. Today, we journey through evidence that challenges our assumptions about permanence, about eternity, about the very meaning of existence in a universe that will eventually forget it ever existed. Prepare yourselves. We begin. In 1998, 2 teams of astronomers made a discovery that would fundamentally alter humanity's understanding of cosmic fate. They were studying supernovae, exploding stars in distant galaxies, using them as cosmic measuring sticks to map the expansion of the universe. The expectation was straightforward. Gravity should be slowing the universe's expansion, pulling everything back together over billions of years. The data showed something else entirely. The universe wasn't slowing down, it was speeding up. Saul Perlmutter, Brian Schmidt, and Adam Rees led these observations. They measured dozens of Type Ia supernovae, stellar explosions so consistent they serve as perfect cosmic lighthouses. By comparing the apparent brightness of these explosions to their actual luminosity, they could calculate precise distances across billions of light years. Every supernova told the same story. Galaxies farther away were receding faster than they should be, not just moving away, but accelerating away, as if some invisible force was pushing the universe apart. They called this force dark energy. Here's what dark energy means. Approximately 68% of everything in the universe consists of something we cannot see, cannot touch, and barely understand. It exerts negative pressure, a kind of anti-gravity that counteracts the attractive force of matter. Think of it this way. Imagine you throw a ball into the air. Gravity slows it down, pulling it back to Earth. But what if, as the ball rose higher, gravity reversed, pushing it upward faster and faster? That's dark energy operating on a cosmic scale. The implications hit the astronomical community like a shock wave. If dark energy dominates the universe, if this mysterious force continues pushing galaxies apart at an accelerating rate, then everything we see in the night sky will eventually disappear beyond the cosmic horizon. Galaxies will race away from us faster than light itself can travel, but the consequences extend far beyond mere cosmic loneliness. Stars require raw materials to form. They need vast clouds of hydrogen gas compressed by gravity until nuclear fusion ignites in their cores. They need galaxies to serve as gravitational wells where this gas can collect. They need the recycling of stellar material through supernovae to enrich the cosmic environment. In an accelerating universe, these conditions cannot persist forever. Fred Adams and Gregory Laughlin, astrophysicists at the University of Michigan, recognized this truth in the late 1990s. They began systematic calculations of the universe's future, dividing cosmic time into distinct eras based on the dominant physical processes. Their work revealed a timeline so vast it makes the current age of the universe, 13.8 billion years, seem like the first femtosecond of existence. We are living in what they called the stelliferous era, the age of stars. This era began approximately 100 million years after the Big Bang, when the first massive stars ignited, and it will continue for trillions of years into the future. But it will end. The death of star formation doesn't happen suddenly. It emerges gradually, inevitably, from the mathematics of cosmic expansion and stellar evolution. Consider the life cycle. Stars form from collapsing gas clouds in galaxies. They burn for millions to trillions of years depending on their mass. When they die, they return material to space through stellar winds and supernovae. This recycled material forms new stars. It's a cosmic cycle that has continued for over 13 billion years. But dark energy disrupts this cycle. As the universe expands, galaxies become increasingly isolated. The space between galaxy clusters stretches. The raw material for star formation becomes trapped in gravitational wells that grow more distant with each passing billion years. Meanwhile, existing stars continue burning, converting hydrogen into helium, helium into heavier elements, steadily depleting the universe's fuel supply. The universe is spending down its energy reserves, and unlike a bank account, these reserves can never be replenished. Recent observations from the Hubble Space Telescope and the Sloan Digital Sky Survey have measured the cosmic star formation rate with increasing precision. The data reveals a disturbing pattern. Star formation peaked approximately 10 billion years ago, roughly 3 billion years after the Big Bang. Since then, the rate has declined by a factor of 10. The universe is already creating fewer new stars than it did in its youth. We exist in a universe past its prime, sliding inexorably toward darkness. The stelliferous era will continue for approximately 100 trillion years, 10,000 times longer than the current age of the universe. During this incomprehensible span, the last generation of stars will form, ignite, and die. But the evidence forces us to confront an uncomfortable possibility. We can trace the timeline of stellar death with mathematical certainty, counting down to the moment when the final star flickers out, leaving the cosmos in perpetual night. The first piece of evidence comes from measuring the universe's expansion rate itself. In 2003, NASA launched the Wilkinson Microwave Anisotropy Probe to map the cosmic microwave background radiation, the afterglow of the Big Bang. The satellite measured tiny temperature fluctuations in this ancient light, revealing the precise composition of the universe. The results confirm dark energy comprises 68% of cosmic energy density. Ordinary matter, everything we can see from stars to galaxies to planets, accounts for barely 5%. Dark matter, the invisible scaffolding that holds galaxies together, makes up 27%. These aren't estimates, they're measurements precise to within 1%. The Planck satellite, launched by the European Space Agency in 2009, refined these measurements further. The data shows dark energy behaves like a cosmological constant, a property of space itself that remains consistent as the universe expands. This constancy carries profound implications. If dark energy's strength varied significantly, the universe might collapse back on itself, or expansion might slow enough to allow continued star formation. Instead, the measurements indicate steady, relentless acceleration. Scientists discovered the second piece of evidence in the distribution of galaxies across cosmic time. The Hubble Deep Field observations, conducted in 1995 and repeatedly refined since, peer into the distant universe by collecting light from galaxies billions of light-years away. Because light travels at finite speed, these observations show us the universe as it existed billions of years ago. Comparing these ancient galaxies to nearby ones reveals dramatic differences. Young galaxies, those we observe as they existed 10 or 12 billion years ago, blaze with brilliant blue light from massive young stars. They're messy, irregular, often colliding with neighbors, triggering intense bursts of star formation. Older galaxies appear redder, more structured, more sedate. Their star formation has slowed dramatically. Many have converted most of their available gas into stars already. The pattern emerges clearly. Galaxies consume their star-forming material at rates that cannot be sustained indefinitely. The third piece comes from studying the smallest, longest-lived stars. Red dwarfs, stars with masses less than 40% that of our Sun, burn hydrogen so slowly they can remain active for trillions of years. Our Sun will die in approximately 5 billion years. A red dwarf forming today could burn for 10 trillion years or more. These miserly stars represent the universe's final phase of stellar activity. When conditions no longer allow massive stars to form, red dwarfs will be the last category to emerge from collapsing gas clouds. Astrophysicists have calculated that the lightest red dwarfs, those barely massive enough to sustain fusion, could theoretically burn for up to 20 trillion years. These stars haven't begun forming in large numbers yet. They'll emerge later as galaxies exhaust their supplies of denser, faster collapsing gas. The implications become clear. We can identify which stars will populate the universe's final stellar generation. We can calculate when they'll die. We can map the end of the stelliferous era with the same confidence that astronomers predict planetary alignments. But this represents just one piece of a much larger puzzle hidden in the mechanics of galaxy evolution. The fourth piece of evidence emerges from observations of intergalactic gas. The space between galaxies isn't empty. It contains diffuse hydrogen, the raw material of star formation. As the universe expands, this gas becomes increasingly dispersed and heated. The Cosmic Origins spectrograph aboard Hubble has mapped this intergalactic medium by studying how light from distant quasars passes through intervening gas clouds. The measurements show the medium is already too hot and diffuse to collapse into new galaxies. Galaxy formation essentially stopped billions of years ago. The galaxies we observe today represent nearly the complete census of star-forming structures the universe will ever produce. New stars will continue forming within existing galaxies as they recycle stellar material, but the cosmic infrastructure for creating additional stellar nurseries has already shut down. The fifth observation comes from understanding stellar mass distribution. Not all stars are created equal. Massive stars, those 10 or 50 or 100 times the Sun's mass, burn ferociously bright but die within millions of years. They contribute disproportionately to a galaxy's luminosity while consuming vast amounts of hydrogen. Small stars burn faintly but persist for eons. As galaxies age and gas supplies diminish, the average mass of newly formed stars decreases. Less gas pressure means smaller, less massive stars emerge from collapsing clouds. Observations of nearby galaxies confirm this trend. Older stellar populations show a preponderance of low-mass stars. The cosmic star formation rate hasn't just declined. The character of new stars has shifted toward longer-lived, dimmer varieties. This represents the universe's transition toward its twilight years, when only the smallest embers remain lit. The most remarkable discovery involves what happens to galaxies in an accelerating universe. Computer simulations run by cosmologists at institutions like the Max Planck Institute for Astrophysics show that dark energy will eventually tear apart large-scale cosmic structures. Not immediately, the process unfolds over trillions of years, but inevitably. Here's why. Galaxies cluster together in groups and clusters held together by mutual gravity. Our Milky Way belongs to the local group, containing about 50 galaxies, spanning approximately 10 million light-years. The local group itself sits on the edge of the Virgo supercluster, a larger structure containing thousands of galaxies. These gravitationally bound structures resist cosmic expansion. The Milky Way and Andromeda Galaxy, for instance, are actually moving toward each other. They'll collide in about 4 billion years, despite the universe's overall expansion. But beyond these local gravitational strongholds, dark energy dominates. Observations of distant supernovae reveal that galaxies beyond our local gravitational neighborhood are accelerating away at increasing speeds. The Hubble Space Telescope has measured galaxies receding at velocities exceeding 50,000 kilometers per second, over 15% the speed of light. As expansion continues, these distant galaxies will cross the cosmic event horizon, the boundary beyond which light can no longer reach us. They'll disappear from view, not because they've been destroyed, but because the space between us expands faster than light can traverse it. In approximately 150 billion years, every galaxy beyond our local group will have vanished beyond this horizon. An observer in the far future, looking at the night sky, would see only the dozen or so galaxies gravitationally bound to our own. The visible universe will shrink to a tiny island of light surrounded by infinite darkness. But the evidence extends beyond cosmic isolation into the realm of galactic starvation. Star formation requires not just hydrogen gas, but specific conditions, sufficient density, appropriate temperature, gravitational compression. Even within galaxies, these conditions don't persist forever. Consider our Milky Way. It currently forms approximately 1 to 2 new stars per year, a rate that sounds modest, but represents billions of stars over cosmic time. This rate has already declined from its peak billions of years ago. Observations from the Atacama Large Millimeter Array in Chile have mapped molecular gas clouds throughout the Milky Way. These clouds represent stellar nurseries, regions where new stars will form. The surveys reveal we have sufficient material for perhaps another trillion years of star formation at current rates. But that material won't all become stars. Much of it will be expelled from the galaxy through stellar winds and supernova explosions. Some will fall into the supermassive black hole at our galaxy's center. Some will be heated too much to collapse. The sixth piece of evidence comes from studying galaxy mergers. When galaxies collide, as the Milky Way and Andromeda will, their gas clouds compress, triggering intense bursts of star formation. These starburst events can consume a galaxy's entire gas supply within 100 million years, creating thousands of times more stars than normal. The Hubble Space Telescope has captured hundreds of these cosmic collisions in various stages. They're spectacular, violent, and ultimately finite. After the starburst exhausts available gas, star formation ceases almost completely. In the far future, after local galaxy groups have merged into single large galaxies, no further collisions will occur. The mechanisms that trigger star formation bursts will no longer exist. The universe will settle into a long, slow decline as existing stars gradually burn out without replacement. The evidence extends beyond star formation rates into the fundamental question of stellar lifetimes themselves. Adams and Laughlin calculated that the least massive red dwarfs, stars with just 8% of the Sun's mass, could theoretically burn for 20 trillion years. But this represents an upper limit based on current stellar models. Recent observations of ancient red dwarfs in our galaxy suggest they may burn even longer. These stars convert only a tiny fraction of their hydrogen into helium through nuclear fusion, using their fuel so slowly that they'll outlast everything else in the cosmos. The last red dwarf will die approximately 100 trillion years from now, over 7,000 times the current age of the universe. After that moment, no nuclear fusion will occur anywhere in the cosmos. The stelliferous era, the age of stars, will end, and the universe will enter a new phase, the degenerate era. The scientific theory that ties everything together is surprisingly simple. Thermodynamics. The second law of thermodynamics states that entropy, disorder, always increases in closed systems. The universe represents the ultimate closed system. Energy flows from concentrated forms to dispersed forms. Hot objects cool. Compressed gases expand. Order gives way to chaos. Stars represent highly ordered concentrations of energy. They fuse light elements into heavier ones, releasing tremendous amounts of energy in the process. But this process cannot continue indefinitely. Eventually, all available fuel will be consumed. This isn't speculation. It's as certain as water flowing downhill. Freeman Dyson, the legendary physicist, explored these implications in a seminal 1979 paper titled Time Without End. He systematically calculated what happens to matter and energy across unimaginable timescales. His conclusions were both precise and disturbing. After the last star dies, the universe will be populated primarily by stellar remnants, white dwarfs, neutron stars, and black holes. These objects no longer produce energy through fusion. They simply radiate away their residual heat. White dwarfs, the collapsed cores of sun-like stars, will cool over trillions of years, gradually fading from white to red to brown to invisible black. Dwarfs, they'll still exist, still contain matter, but they'll be completely cold, completely dark, completely inert. Our sun will become a white dwarf in approximately 8 billion years. It will then cool for 100 quadrillion years before becoming a black dwarf. An object that doesn't yet exist anywhere in the universe because the cosmos isn't old enough for any white dwarf to have cooled completely. Neutron stars, collapsed cores of massive stars, follow a similar trajectory. They'll radiate away their heat, spinning slower and slower as they lose rotational energy, eventually becoming cold, dark spheres of degenerate matter just 20 kilometers across, but containing 1.5 times the Sun's mass. This forces us to reconsider fundamental assumptions about permanence in the cosmos. Nothing lasts forever. Not stars, not galaxies, not even atoms. Current theories of particle physics suggest that protons, the fundamental building blocks of atomic nuclei, may not be stable over extremely long timescales. If protons decay, then all ordinary matter will eventually dissolve into radiation. The estimated proton half-life exceeds 10^34 years. That's 1 followed by 34 zeros, a number so large it defies comprehension. But even at this glacial pace, all matter in the universe would eventually decay. Experiments at facilities like the Super Kamiokande detector in Japan have searched for proton decay without finding evidence. This sets a lower limit on the proton lifetime, but doesn't rule out eventual decay over truly cosmic timescales. If protons are stable, the universe will be dominated by cold stellar remnants essentially forever. If they decay, even these remnants will evaporate into radiation. Either way, the age of stars, our age, represents a brief anomaly in cosmic history. Recent breakthroughs suggest we're entering an unprecedented era of cosmic archaeology. The James Webb Space Telescope, launched in 2021, observes infrared light, perfect for studying cool, dim objects. As the universe ages and stars die, infrared astronomy will become increasingly important for studying stellar remnants. Webb has already captured images of the earliest galaxies formed after the Big Bang. These observations help calibrate models of how star formation evolved over cosmic history. Each observation adds data points to our map of stellar decline. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will conduct extensive surveys of dark energy to measure how cosmic acceleration evolves over time. These measurements will refine our predictions about when the last stars will form. Ground-based observatories like the Vera C. Rubin Observatory will catalogue billions of galaxies. mapping star formation rates across cosmic time with unprecedented precision. What technologies might help solve remaining mysteries? Gravitational wave astronomy, detecting ripples in space-time from colliding black holes and neutron stars, provides new windows into stellar death. The LIGO and Virgo detectors have already observed dozens of these cosmic collisions. Future space-based gravitational wave observatories like the Laser Interferometer Space Antenna will detect mergers of massive black holes, probing the final stages of galaxy evolution when central black holes consume remaining matter. These observations help answer practical questions. How efficiently do galaxies convert gas into stars? How much material escapes into intergalactic space? How do supermassive black holes affect their host galaxies? Each answer refines our timeline of cosmic decline. The implications connect to broader questions about the universe's ultimate fate. If dark energy remains constant, the current best evidence, then the universe will continue expanding forever. This scenario, called the Big Freeze or heat death, results in a cold, dark, empty cosmos. Alternative possibilities exist. If dark energy strengthens over time, it could eventually overcome gravity on all scales, tearing apart galaxies, solar systems, even atoms, in a big rip. Current observations suggest this isn't happening, but uncertainties remain. If dark energy weakens or reverses, cosmic expansion might slow or even reverse, resulting in a big crunch where everything collapses back together. Most evidence argues against this outcome. The observations point toward the same conclusion: continued expansion, cosmic isolation, and eventual heat death. What this means for us, for humanity, depends on timescales that dwarf our existence. Life emerged on Earth approximately 4 billion years ago. Human civilization began roughly 10,000 years ago. Recorded history spans about 5,000 years. The Sun will die in 5 billion years, 1,000 times longer than life has existed on Earth. The last star will die in 100 trillion years, 20,000 times longer than that. These timescales are so vast they render our existence cosmically insignificant. The entire history of life on Earth, from the first bacteria to the distant future when our descendants might populate other worlds, occupies the tiniest fraction of the stelliferous era. We exist in a universe of light, but we're witnessing its twilight. Yet this knowledge carries profound meaning. We are the universe become conscious of itself. We are matter contemplating its own fate. In this cold cosmos governed by thermodynamics, we represent pockets of temporary complexity, brief flames of consciousness burning against the encroaching dark. Act 4, The Ultimate Questions, 50 key 58 Sulati. The most profound implications emerge when we consider what the universe will contain after stars cease to exist. Imagine a cosmos 100 trillion years from now. No stars shine. Galaxies have completed their final mergers, forming isolated supergalaxies separated by expanding voids of emptiness. Each supergalaxy contains white dwarfs, neutron stars, black holes, all cold, all dark, all slowly evaporating. The temperature of space itself approaches absolute zero, not the 2.7 Kelvin of today's cosmic microwave background, but a fraction of a degree above the lowest possible temperature. In this environment, bizarre physics becomes possible. White dwarfs, those cooling stellar corpses, will occasionally undergo quantum mechanical events. Despite being cold and inert, they contain enormous numbers of atoms. Over sufficient time, quantum tunneling can enable fusion reactions even at these impossibly low temperatures. The physicist Fred Adams calculated that two white dwarfs might merge through gravitational perturbations, creating enough heat to reignite fusion temporarily. These events would be extraordinarily rare, occurring once per galaxy per 10-100 years, but they would create brief, final flickers of starlight in the dying universe. This time scale, 10-100 years, is called a googol. It's 1 followed by 100 zeros, a number larger than the total number of atoms in the observable universe today. Even considering such vast timescales, these fusion events would be finite. Eventually, no fuel remains. The last flicker of nuclear fusion would occur, and darkness would reign supreme. But black holes complicate this picture. Stephen Hawking predicted in 1974 that black holes aren't truly black. They emit radiation through quantum effects at their event horizons. This Hawking radiation causes black holes to slowly evaporate. The timescale depends on mass. A black hole with the Sun's mass would take 10 to 64 years to evaporate. A supermassive black hole, like the one at our galaxy's center, containing 4 million solar masses, would persist for 10 to 87 years. Eventually, every black hole would disappear in a final burst of radiation. The universe would be left with dilute radiation, cold stellar remnants, and perhaps elementary particles if protons prove stable. The temperature would approach absolute zero, entropy would approach its maximum. Nothing would happen anywhere ever again. This is heat death, the ultimate destiny predicted by thermodynamics. What the evidence suggests about reality itself challenges our deepest intuitions. We perceive the universe as permanent, stable, eternal. Stars shine, galaxies spiral. Life emerges and evolves. The cosmos seems designed for existence. But physics reveals a different truth. We inhabit a temporary oasis of complexity in a universe sliding toward equilibrium. Stars represent unstable configurations, nuclear fusion in violent balance against gravity that cannot persist forever. The age of stars is finite. The age of darkness is eternal. This doesn't make existence meaningless. If anything, it makes existence more precious. We are witnessing the universe in its golden age. We see galaxies ablaze with starlight. We orbit a star that provides warmth and energy. We exist in conditions that will never occur again once they pass. The question becomes, what do we do with this knowledge? We've traced the evidence from the 1998 discovery of cosmic acceleration to the mathematical certainty of stellar death. We've examined the declining star formation rate, the isolation of galaxies, the cooling of stellar remnants, and the ultimate heat death of the cosmos. The timeline extends across unimaginable spans, 100 trillion years until the last star dies, 10,000 years until the final flicker of fusion, 10,406 years until the last black hole evaporates. These aren't just big numbers. They're the measured, calculated destiny of everything. What we've learned is this: the universe is spending down its energy reserves. Dark energy accelerates cosmic expansion, isolating galaxies and halting star formation. Existing stars burn through available fuel, gradually dimming. Even after they die, their remnants cool until they're indistinguishable from empty space itself. What remains unknown, the precise nature of dark energy, whether protons decay, whether any physical processes could generate new complexity in the far future, whether our current understanding of physics remains valid across such enormous timescales. The current scientific consensus holds that cosmic heat death represents the most likely outcome given available evidence. The universe will expand, cool, and darken until nothing happens anywhere ever again. But consider what we've witnessed in our brief moment of consciousness. We live in a universe 13.8 billion years old, barely 0.014% of the stelliferous era's duration. We've existed as a species for 300,000 years, an eye blink in cosmic time. Yet in this impossibly brief window, we've deciphered the universe's structure, measured its expansion, calculated its fate. We are matter contemplating its destiny. We are the universe's way of understanding itself. The cosmos will grow dark. The stars will die. The galaxies will vanish beyond the horizon. Eventually, nothing will remain but cold remnants radiating into infinite emptiness. But right now, in this fleeting moment, the universe blazes with light, and we are here to witness it. The universe is vast, the darkness is patient, but the stars still shine.